Hello. In this video, we are going to look at how to do a power analysis for a factorial ANOVA. So for starters, we're going to be using the superpower package, which is really awesome because it's going to let us compute power for everything all at once. Main effects, interactions, simple effects. In real life, when we run a factorial study, we're often invested in the power for all of those different things. Or depending on the inferential goals of our particular study, we might care about one set of simple effects more than another, or we might want to make sure we have power for a main effect, but we don't care about the interaction, or vice versa. This tells us, if we give it a set of assumptions about the population and the sample size, it'll tell us what we can reasonably expect our power to be under those assumptions for all of them at once. So unlike, say, G-power, where you can only compute power for this effect in isolation or that effect in isolation, here we get an awesome bird's eye view of all of the tests that we could want to run in our design. So it's a very informative approach. So for starters, we're going to create this object here, giving it all of the information about our design, and we're going to call it design setup. And then once we've done that, down here, we're going to use design setup to actually compute the power. Not as tricky as it sounds. Let's just go through one step at a time. So for starters, we have to tell it our design, and this is a 2x3 between subjects factorial design, and we designate that with this string here, 2b by 3b. We have two factors, each between subjects. The first has 2 levels, the second has 3 levels, so it's a 2x3 between subjects. Now, here I've told it n equals 100 per condition. So we have 6 conditions. That means there's actually 600 people in this design. Now, 600 people, that's not as crazy as it sounds. When you're computing power for statistical interactions, it's actually very humbling. You often need 600 or more people to detect even modestly sized interactions. Conveniently, we can give it the names of the different factors and levels we're working with. That makes the output a lot easier to read. In this case, I'm imagining we're looking at the effects of being included versus ostracized versus a control condition. And we're going to look at whether that depends on if the person you're interacting with is a stranger versus a friend. And I'm going to set the standard deviation across all conditions to be 1. And the reason that is a convenient thing to do is because that means when I set up the means in the population here, when I set the standard deviation to 1, it means that the differences between means are in units of standard deviation. In other words, Cohen's d. So we can use standardized effect size metrics here to look at our results. Now, the pattern of means corresponds to the labels in the design up here, but it's always tricky for me. I have to use a lot of trial and error because there aren't labels here. And so when you run it, you get a graph, which is really helpful because it can allow you to confirm with your own eyes if you set up the pattern of means that you really intended to. And so let's look at what I'm asking us to imagine in this case to be true about the population. So suppose the population means contain an interaction like the one we're looking at here. I'm imagining that when you're talking to a stranger, the difference between being ostracized versus included or a control event is a Cohen's d of 1, a very large effect. You're talking to a stranger, it hurts your well-being by an entire standard deviation, let's say. However, I'm imagining that it depends on the type of person you're talking to. If it's a stranger, it hurts a lot. But if you're talking to a friend, maybe it doesn't hurt so much. You know this person, you go back years, you know you're going to be talking to them again soon, and maybe you'll be the one ignoring them. So hypothetically, let's suppose that in the population, the effect of this treatment variable is only half as large for friends versus strangers. So what that means is up here, I've set it up so that the difference is only half a standard deviation between in this case, the included group and the ostracized group. So see, the included group is half a standard deviation higher than the ostracized group, which has a mean of 0 here. So this pattern of means corresponds to the interaction that I've laid out here. It's not a particularly small interaction. All I'm saying here is that the effect is twice as big for strangers versus friends. That's not a small interaction. You can see here I'm laying the groundwork because we're going to see power is not as great as we'd want it to be even with 600 people. That's the sad reality of powering interactions often. So with all of this set up, we can ask, with 600 people, what is our power? So we save design setup to this object, and we input it to ANOVA exact with an alpha level of 0.05, and we can print the result, and it shows us what our power is for the main effects, the interaction, and all possible simple effects here, which is quite a lot of output. You kind of have to go hunting for the effects you care about, but they are all there. But let's start with the main effects and interaction, which are printed right here at the top, front and center, which is convenient. So our power for the main effect of a person, whether you're talking to a stranger or a friend, is very good in this case. Given the means I've entered, we're very likely to detect that effect. It also gives us the partial eta squared that is implied by the pattern of means that I asked us to imagine is in the population earlier. So assuming this pattern of means I laid out here, the partial eta squared for that main effect is explaining 3% of the variance. Pretty cool. Condition, we have virtually 100% power to detect the main effect of condition. That's great, but I think you realize the purpose of this study is not to detect the main effect of condition. There's really nothing surprising about ostracism hurting people's needs. We know that's the case. What really is likely the purpose of this study is to detect an interaction effect. I want to know, does it depend on whether you're interacting with a stranger versus a friend? Well, in that case, with 600 people, and an interaction effect such that the effect is twice as large for strangers versus friends, we'll find a significant effect 73% of the time. Okay, I mean, it could be a lot worse, but it's not super encouraging. A quarter of the time, even if you're right in the population there's an effect, you're still not going to detect it. Well, that might cause you to rethink your design, look at whether some of the factors can be switched to within subjects or not. You can think about things like pre-registering covariates or particular one-tailed tests. You know that there are many ways to try to improve power. The most obvious, of course, is painful, but it's increasing sample size, which you could do. So if we wanted to get this up to 80%, we could try inputting different sample sizes to see how many we'd have to run to have an 80% or a 90% chance of detecting this interaction effect. We might also look into collapsing levels of the design, included and control groups. Maybe we know from prior research that those two are similar enough that this particular study doesn't need both of them. So maybe we'd choose to make this a 2x2 instead of a 2x3, and we might be able to walk away with a smaller total sample size and still have a good chance of an interaction effect. So my point here isn't to depress you, it's just to illustrate some of the thought process you might go through when you're thinking about ways to plan a study so that you're likely to have an informative result at the end of it, because here it's not necessarily the case. So we looked at the main effects and the interaction. Down here below that, I'm going to rerun this so it prints with the results side by side like I'd like. Down here below that, we have the power and the Cohen's d effect size. Again, because I entered the standard deviation as 1, the effect size is already in Cohen's d, but here it would have converted it, which is nice. We have all of the simple effects or the pairwise comparisons we could care about. So for example, when you're in the stranger condition, the control versus included conditions, there's a lot of unnecessary strings here, so you have to read it kind of carefully to see which two conditions are being compared. The power for control versus included in the stranger condition is just 5%. Now that makes sense because above I specified that those have the same mean, so the power for that is irrelevant. There's no difference. Whereas if we're looking at, again, in the stranger condition, the difference between control versus ostracized is approaching 100%. with a standard deviation of 1 for that effect size. So the power for that simple effect is really strong, which is great if that's something that we really want to detect. And then if we go down to just the friend conditions here and we look at the power for control versus included, again, that's just 5% for the same reason. Things get more interesting when we look at control versus ostracized. We see power for that is 94% for that particular simple effect, which is a Cohen's d of 0.5. So we will find that simple effect most of the time if we run this study, which is great. Maybe, unlike my worrying before, maybe we don't care about the interaction effect all that much. Maybe we just want to make sure we have a big enough power to detect the simple effects in the particular cells we care about. If that's our goal, then this output is reassuring. This means maybe we could proceed with this study. We shouldn't expect to find the interaction every time, but we do have good reason to think we'd find the simple effects we care about each time. If that's what we want to do, then that's a green light to proceed. So hopefully you can see some judgments involved, and this tool gives you all of the information you need to make an informed judgment. Okay, so I think you get the idea. One last thing I'll point out is just like before, you might be in a situation where you don't expect to have the same number of participants in each condition of your design. It might be for practical reasons. You can only access so many of particular subpopulations. If you're studying left-handed people, it's going to be harder to get a sample of left-handed people than it is for right-handed people, so you might expect far more of one than the other. You can calculate power assuming different n's per condition using this approach here where you give the same sorts of information, except for now you give particular n's per condition. The only difference is down here when you run the power computation itself, we're going to use a simulation approach using ANOVA power. And when you do that, you buy the ability, it takes longer because it has to simulate it, but you buy the ability to input different n's per condition. So I can run exactly what we ran above with 600 participants, assuming the same number per condition. And it takes a minute to run because it's simulating, but when it's done, it'll give me results that approximate what we got earlier. And while it's thinking, I'm going to go ahead and just type in what I imagine to be the case for when we run this later. Okay, so looking down at our output, we see results that are very similar to what we saw above. This is good. Now, imagine I'm worried about power for the interaction effect, so I want to increase my sample size. But suppose we already know that ostracism hurts when it's a stranger who's ostracizing you, but imagine we know far less about when it's a friend ostracizing you. And so I want to increase my sample size, but maybe I'm going to over-assign people. I'm still going to randomly assign them. I'm just going to set up the randomization so that more of the people are assigned to these friend conditions, because that'll increase my power for the conditions that we know less about. So I get extra precision for the cells in the design that I'm extra interested in investigating. There's no reason not to do that if it's something that I care about. So here I can say I'm going to add 150 people to my design. I'm going to do an extra 50 in each of the 3 friend conditions. Well, now I can see how that affects my power for the main effects, the interaction, and the simple effects. So we can go ahead and run this, and again, it'll take a little minute. This is when I like to go get coffee or an energy drink and meditate, engage in some mindfulness here. Become comfortable with silence, whatever you got to do. Oh, hey, look at that. We've got our result. And we can see I've increased our sample size, 150 participants, and that's good. Our power for the interaction has gone up. Now, it actually would have gone up more if we assigned those 150 equally across the 6, but because we concentrated them in these 3, we're not maximizing for the interaction here. We're actually maximizing for the simple effects involving these three groups. And if that's what we want to do, then great. But still, of course, more participants never hurts your inferences, and we see that our power for the interaction has gone up a little bit, which is great. I won't say no to that. But the real benefit is, here, I'm just going to reprint this because I want those side by side. Good. The real benefit is when we look at power, again, for those simple effects involving the friend conditions. Before, the power for those was 98, 99%. Wait a second. No, that was for the most recent one, so we got to go further. That was around 94%. Not bad, but maybe you want to scoot it up even higher. I'm just illustrating the benefits of concentrated assignment to certain conditions here. Well, 94 could be higher, and in fact, we see that if we add 50 to each of those conditions, it goes up to 98, 99%, which is really good. So you can imagine cases where your sample sizes are even smaller to begin with, and in those cases, you might be going from 60 or 70% up to 80 or 90% by putting people just in those conditions you care more about. Cool. So my point here obviously is not to say that you have to do this, or even that it makes a big case and a big difference in this case. Here it doesn't make a huge difference. The point is you have all the tools you need to answer all of the questions about power under different assumptions of sample size and mean differences in the population. So there you have it. Next time we will look at how to compute regression analysis, and I will see you then.